Good evening. Today we are going to design a continuous floor beam by IS code coefficient. Now we have designed floor beam ABCDE as shown in figure. The depth of slab is 120 mm and monolithic with the beams. The beam have width 250 mm, floor finish 1.5. Superimpose load 4, use M25 and FE415 and floor to floor height is 3.5. So we have to design this beam A, B, C, D, E. Now we have to see we have this as 4.5 and then we have this as 4.25. So we have maximum as 4.5 and minimum we have 4.25. So we can go for 4.25 divided by 4.5 and then we will get it as 4.25 divided by 4.5 and we have this value 0.94 which is greater than 0.85 and so we can use IS code coefficients. And by using IS code coefficient we can design this beam which is given in table 19 in IS 456. No, sorry, we have that is don't remember, but that is we have in IS 456 these coefficients. So I think table we have 12 for flexure and 13 we have for shear. So now we have effective span, that is L effective maximum span 4500, trial depth we have upon 13. Now we have taken upon 13 because we have slab on both sides. And then we will provide it 346.14, so plus 40 386.15 millimeters. So provide D 400 and small d 360 millimeters. So same depths we have. Load calculations we have same dead load from slab, weight of wall, self weight of beam. Now load transfer of slab to beam ABCD as follows. So we have this will be trapezoidal. We have to convert triangle. Same for all. We have triangular load on this because we have all these as a two-way slab and we have triangle on this side because if you will see this plan, then we have this as 5 meters and we have this as 5 meters. So both we have 5 meter. So uh, load we have in the same way whatever we have shown for first slab. So that is likewise. So in all slabs we have in this fashion and therefore we have triangular load on both sides. So A, B, C, D, E. So now we will start with load on beams A, B and C, D. Now why we will go for A, B and C, D? Now if you will see we have dimensions span of A, B and span of C, D is same. And these two are different. So we will have to go BC 4.25, D 4.35 and then we will go likewise. So we have 25 D thickness, we have 0.12, so 3 plus 1.5, 4.5. So now we have taken twice because we have same triangular load on both sides. So we have triangular load on both sides of beam and therefore we have considered it as twice WLX by 3. So 4.5 that is W, we have WUD and 4.5 span upon 3 13.5 kilonewton per meter. Weight of wall we have 20 B into H, floor to floor height 3.5 and depth of beam we have 0.4, so we have 15.5 kilonewton per meter. Then we have 25.25, 0.4 minus 0.12. This 0.12 we have depth of slab which we have subtracted from depth of beam and we have 1.75 and total dead load we will get it as 30.75 kilonewton per meter. Now we will make it factored. So we have 1.5 into 30.75. So we will get it as 46.13. So I will make it as 46.1 kilonewton per meter. Now factorial live load we have again twice 1.5 WLX by 3. So 2 into 1.5 W we have 4 which is live load into 4.5 by 3. So we have 18 kilonewton per meter. Now we will go BC. Now we know for BC these things we have as it is. Only we have change in WX which will be 4.25 remaining all same. So we have weight of wall we have same. Then we have self weight of beam we have same 1.75, and then we have this value as 30 kilonewton per meter. So change we have only from slab. So you can see this, we have here also 15.5 and 1.75, and same values we have here 15.5 and 1.75. So 30 into 1.5, 45 kilonewton per meter. So 2 into now WLX again 4.25, so it will give me 17 kilonewton per meter. Now I will calculate, that is for DE. Now here we have this value again we have same, then change we have in LX which is 4.35, and from this 4.35 we will get 13.05 kilonewton per meter. Then these two value as it is, so we will get dead load 30.3 and factorial dead load 45.45, and factorial live load we have 17.4 kilonewton per meter. And now we will go with bending moment. So this is, you can see we have this as table 12. So by mistake I mentioned it as 19 first, but afterwards we have written 12. So we have table 12 bending moment coefficient. We have span moments near middle of end span at middle of interior span. And then we have this for support. First we will go for span moments. Then we can see alpha D. We are considering these two because we are with span moment. So 1 by 12, 1 by 16, 1 by 10, 1 by 12. So now you can see this. So we have this A, B, C, D, E. So if I will mention this, we have A, B, C, D, E. So we can have this A, B, C, D, E over there. And now you can see these values. That is 1 by 12 near middle of end span, 1 by 16 at middle of interior span. This is also middle of interior span 1 by 16, and for D which is near middle of end span. So for near middle of end span we have these two, and at interior we have these two. So 1 by 12, 1 by 16, 1 by 16, 1 by 12. And for dead load we have now actually values we have different, so we will not consider this 46.1. If we will take span same, then we will have this value. Now for live load we have 1 by 10, 1 by 12. So now you can see 1 by 10, 1 by 12, 1 by 12, 1 by 10. So this is also not 18 now. And then we are with these values. So we have to add this for maximum bending moment, and we have to multiply. You can see WUD L square, then WUL square. So alpha D, alpha L. So we have these coefficients. Then we will go for now important we have if we have span that is different, then we have to take average, and if we have load different, then also we have to go average of the load, and that we have to consider. If we will go below table 12, then you will come to know these values. So now we have maximum bending moment at mid span of AB. Now we have dead load for AB we have 46.1, and span we have 4.5. So we have here, you can see we have 1 by 12 and 1 by 10. So two only we have, 1 by 12, 1 by 10, which will be end, and interior we have 1 by 16 and 1 by 12. So now we will go here 1 by 12, 46.1 into 4.5 square. Plus 1 by 10, 18 into 4.5 square. So 114.24. For BC 1 by 16 and 1 by 12 values we have different, WUD and span also. Then WUL and span also. So 76.39. Similarly for CD we have 86.73, span though 45.4.5 square, 46.1 plus 1 by 12 into 18 into 4.5 square. Now here we have 1 by 12, 1 by 10, and interior we have 1 by 16 and 1 by 12. So though load and span are same, but our coefficients are different. And last we have, that is DE. We will have this as end span. So 1 by 12 and 1 by 10, 104.6. So maximum value we have 114.24 kilonewton meter, that is positive moment or at mid span or sagging moment. So we can have these values. Now you can see we have bending moment due to dead load, these values. Due to imposed load, we have these values, and these we have final values. And maximum value we have over here 114.24 kilonewton meter. Now we will switch over to support moment. So we have at support next to the end support minus 1 by 10 minus 1 by 9, and interior support minus 1 by 12 minus 1 by 9, minus 1 by 9 for live load as it is, only change in dead load. So minus 1 by 10 minus 1 by 10. At end support we have moment 0, so we need not require to calculate for this. So now alpha D we have these values, alpha L we have these values. So for alpha L we have both minus 1 by 9 minus 1 by 9 for next to end support and at other support also. So now we will go likewise. So you can see, so we have at support next to end support. This is my end support. This is my end support. So next to end support. So we have these two supports. So we have minus 1 by 10. And then at interior support, at other interior support, we have minus 1 by 10. Then live load we have all minus 1 by 9. So you can see this. All supports we have minus 1 by 9. So we have to add this, and from this we will get maximum moment. Now we have dead load on this side, different dead load on this side. Means if I will say we have, this will be A, B, C, D, E. Then for support B, I have to take average of A, B and BC, span and load. For C, we have to take average of BC and CD for both load and span. And for D, we have to take average of CD and D. And that we have calculated over here. So you can see, so maximum bending moment next to support A. So we have this next to support A, and then we have this value minus 1 by 10, 46.1 plus 45. So this is dead load of AB, this is of BC by 2. This is span of AB, this is of BC. And from this we will get this MU1 value. So MU1 actually we have 124.4 kilonewton meter. So we have this value 124.4 kilonewton meter. Now similarly we will go for support C, then we have this value will be for BC, this value we have for CD, this is span BC, this is span CD. Same way we have here WL for BC CD, and same we have for span, we will have this value 109.87 kilonewton meter. And then we have that is maximum moment next to support, so we have E. So this is support. So if I will mention the support directly, then we have this value at support B. Then we have this will be interior support, which is at support C. And then we have last. So this we have that value is at support D. So we have this is at support D, and then we have these values. These values we have mentioned over here. So we have these as A, B, C, D, E. Now you can see these spans, and then we will put the values. So we have this will be minus 87.19 due to dead load, and due to live load we have minus 37.21, and we have this value that is maximum value minus 124.4 kilonewton meter. So this is, these values are from dead load, and we have these values are from live load. So for imposed load we know we have same coefficients. For dead load we have next to end support we have minus 1 by 10 and interior minus 1 by 12. If you will see, then we have these values, that is minus 1 by 12 and interior minus 1 by 12. And likewise we will get these values of the moment. Once we know moment, then we can find depth from bending moment consideration. So Ku max for Fe415, Ru max for Fe415 M25, we have 3.45. And then from this, if we will calculate D required, we have this value 385.46 millimeter. We have provided 360. So this value we have. So this is not okay. Then what we have to go for? We have to provide value of D, small d 390 and capital D 440. So you can see this 390 we have provided, and we have here 385. Now we need not require to go back and calculate the values. So there is very small difference between the values due to 360 and due to 390. So do not go back and calculate it, but we should know, we hence after whenever we will go for calculations, we have to take value whichever we are providing due to the bending moment consideration. So this is all about your IS coefficients. Now I have not taken in this, that is reinforcement and all that you can find, because we already know if we have support moment, we have at top, we have span moment, we have at bottom. So for this we will stop here only. Here also we have not considered shear force calculations. We may go in other any video. So we will stop here only. So thank you.